Okay, for Calculus, Chapter 6, Section 6. We're going to be looking at complex numbers. Remember, complex numbers have a real part and an imaginary part to them. So 2 is the real, 3 is the imaginary. Back in Algebra 2, we were introduced to the complex plane where we can graph complex numbers. Instead of having an x and y axis, the complex plane has a real axis for the horizontal and an imaginary axis for the vertical. So if we wanted to graph the number 2 plus 3i, 2 is the real value, so I go right 2 in the real direction. 3 is the imaginary value, so we will go up 3 in the imaginary direction. And we arrive at this location, 2 plus 3i. Example 1. Plot point U, which happens to be 1 plus 3i. Real axis, imaginary axis, right 1, up 3, there's the point U, 1 plus 3i. V, 2 minus I, right 2, down 1. There's V, 2 minus I. So this was 1 plus 3i. This was 2 minus I. Then it says, after we plot them, do U plus V. Well, let's take 1 plus 3i. Let's add to it 2 minus I. And I get the real part of 3, the imaginary part of 2i, 3 plus 2i. 1, 2, 3, 1, 2. Right there's the location of 3 plus 2i, which is the sum of U plus V. It says these 3 points and the origin determine a quadrilateral. Is the quadrilateral a parallelogram? Well, looking at it, sure kind of looks like it is. In fact, we could look at the slopes of each of these sides. I could get the slope just rise over run, up 3 over 1, a slope of 3, and this opposite side to it, up 3 over 1, a slope of 3, and we could do the opposite sides. Yeah, sure enough, it is a parallelogram. There's another way of looking at that. Right down here is the same plot. If we change these into a vector, go from the origin to point U, that would be the vector 1, 3. And then down here, our point V, the vector 2, -1. And the resultant of the two is the vector 3, 2. Well, we know the resultant right over here with the parallelogram method is just that diagonal. And the resultant is the sum of these two vectors. Well, a minute ago we just took the sum of the complex numbers. We do the same process to take the sum of vectors. I add the x parts, 1 plus 2, that would be 3. And then 3 minus 1, that would be 2. That would be the sum of those two vectors, vector 3, 2. And there it is. The parallelogram method means it works as the diagonal of a parallelogram. Absolute value, or the modulus of a complex number. Remember what absolute value is. It's the distance we are from 0, if it's on the number line, or the distance we are from the origin if we are in a plane. So the absolute value of a complex number is the distance we are from the origin. So if we think of a complex number, and we often use the letter Z to stand for some complex number, A plus BI. Let's look right down here at this graph for a moment. A plus BI, here's the point Z, A plus BI, which means I've gone A to the right and B up, B in the imaginary direction. Well, that forms a right triangle. And if my legs are A and B, then the Pythagorean theorem tells me that hypotenuse, or the radius, the distance we are from the origin, which is also called the absolute value, or the modulus of the complex number, the Pythagorean theorem would find that for us. It would just be the square root of A squared plus B squared. And sure enough, right up here, the absolute value of a complex number, the absolute value of A plus BI, is found just using the Pythagorean theorem. Square root of the real number squared plus the imaginary value squared. And we're not squaring the I, it's just the 3, the coefficient, the B value that goes with it. Now, we have a way of writing complex numbers in what is called trigonometric form, or polar form. And we have just gotten through graphing polar equations. So we're going to be using our trig functions, sine, cosine, etc., in the trigonometric form of a complex number. So standard form is that A plus BI. Complex number in standard form is going to look like A plus BI. So how can I convert that into a trig form? A trig form is going to deal with the radius, the distance from the origin, and an angle. So if we come back to our diagram over here on the right, it's going to deal with the radius and the angle. Standard position angle there. Well, we know in a right triangle, if I know the radius or the hypotenuse, how to get the adjacent side down here. It's just the hypotenuse, the r, times the cosine of the angle. So the A is r cosine angle. And the B, the opposite side from that angle, r sine of the angle, r sine theta. So if I want to write A plus BI in complex form, well, to get the A, it's r cosine theta. If I want to get the B, it's r sine theta, and then there's an I tacked on here. But we could do a little factoring. There's an r in both of these terms, and so if I factored out the r, I'd be left with cosine theta plus, then I'm going to throw the I in first, just rearrange it, I sine theta. And that is considered the trig form or polar form of a complex number. So right down here, trigonometric form is just r parentheses cosine theta plus I sine theta. And how do we get that? Because the A is r cosine theta, the B is r sine theta, and r is the square root of A squared plus B squared. How would I get the angle? Well, tangent of the angle is B over A, so I know I can take the inverse tangent of B over A and I can get that angle. And remember, r is called the absolute value of the complex number, or it's called the modulus of the complex number. And the angle is called the argument. So the direction angle is the argument of a complex number. So when we're talking about complex numbers, we have something called the modulus, which is the absolute value, the distance from the origin, and we have something called the argument, which is the angle. So r is really the modulus, and theta is the argument. Example 2, find the trigonometric form with angles between 0 and 2 pi for the following complex numbers. 1 minus square root of 3i. So if we look at a graph, over 1, down square root of 3, negative square root of 3 in the imaginary direction. Well, we can recognize this as one of our special triangles. 1, 2, square root of 3. And that angle right there is a 60-degree angle, except we probably don't want it in degrees, pi over 3. So our angle in size is pi over 3. Now, a couple ways we could write it. We could write it as a negative pi over 3, but standard position angles are counterclockwise from the positive x-axis. So we're pi over 3 short of a full circle. So if 6/3 is a full circle, it's 5/3 pi. So my angle is 5/3 going all the way around. I need to know the radius, the modulus, 2. I need to know the angle, 5π/3. And so I can write it in its trigonometric form, which is that r cosine theta plus I sine theta. So it is just 2 parentheses cosine 5π/3 plus I sine 5π/3. Trig form. Part B, -3 minus 4i. So I know I've gone back 3, distance of 3, -3. I know I have gone down 4, distance of 4. I can find the r. Well, you might recognize 3, 4, 5. It's a 3, 4, 5 triangle. There's our value of r. Now I need to get my angle inside here. Well, that is not a special triangle, so that is not going to have an exact value for us. So I can get that theta prime, the angle inside the triangle, by taking the inverse tangent of opposite, -4, over adjacent, -3, and of course a negative divided by negative is a positive. So an inverse tangent of 4/3, approximately 0.93. Now I need to get the standard position angle, so all the way around to there. Now this 0.93 is in radians. We're in radian mode here, and if not, make sure you change your calculator to radian mode when you take that inverse tangent. So if you took inverse tangent and you didn't get 0.93, you're probably just in the wrong mode. So I need to add to that pi, because halfway around my circle is pi, plus that 0.93. So we need to add to this pi to get the true angle. Okay, we're ready to write it. We have a radius 5, parentheses. And if I add these together, I guess we'll want a number. It's approximately 4.07. Cosine 4.07 in radians plus I sine 4.07. There's our trig form of this one. Not an exact value because we don't have a special triangle. If I have a special triangle or a quadrantal angle where I know the exact value, then write it with the exact value for that angle, such as in part A. So how do we take the product and quotient of complex numbers when they are in trig form? How do I multiply them? How do I divide them? So they're saying, all right, z sub 1, one complex number here, subscripts 1, z sub 2, second complex number is here, then how do I find the product of those two? Well, it happens to be very easy. I just multiply the moduli, the radii, together, and I add the angles together. If I am dividing, very similar. If I want to divide the two numbers, I divide the moduli, and I subtract the angles. So let's try them out on example 3. Express the product of z sub 1 and z sub 2 in standard form. Now they've started us with trig form. We're going to use the trig form to multiply them together, and then we'll translate the trig form back into standard form. Remember, standard form is a plus bi. All right, so if I use the trig form and I multiply it together, well, I first need to multiply the two radii, or the moduli, together. So if I multiply 25 squared to 2 times 14, we get 350 square roots of 2, parentheses, cosine. Now I need to add those angles together. So we need to take a negative pi over 4 and add to it a pi over 3. Well, if I'm going to do that, I need a common denominator of 12, don't I? So change 4 to 12, we multiplied by 3, negative 3 pi. 3 to 12, we multiplied by 4, 4 pi. So negative 3 plus 4 pi, pi over 12. Cosine pi over 12 plus I sine pi over 12. There it is. There is our product. Oh, we need to convert it, don't we? So we found our product. It's in trig form. Now they ask for us to place it into standard form. So we're going to need to convert it back into the a plus bi. Well, remember that a is r cosine theta, and b is r sine theta. So my r is this. I just need to take 350 square roots of 2 times the cosine of pi over 12, and I will know what my a value is. So it's really just distributing that trig form. Make sure you're in radian mode. You should get 478.11 for the a, r sine theta. So 350 square roots of 2 times the sine of pi over 12, 128.11. That's the b value. So standard form, 478.11 plus 128.11 I. There is the standard form of that solution. Dividing complex numbers. So we want to take z sub 1 divided by z sub 2, and again end up in standard form. We are done. Okay, so if I'm going to divide, well, the radii, 2 square roots of 2, the moduli, over 6. Well, that reduces to square root of 2 over 3. Then my angles, I need to subtract. So I need to take the first one, 135, minus the second one, 300. Now notice they've switched here to degrees. We'll have to remember that when we are working on this. So that gives us negative 165. So our quotient is square root of 2 over 3 cosine of negative 165 plus I sine of negative 165. So there's our answer in the trig form. They want us to convert to standard form. So really it's just distributing here. Square root of 2 over 3 times the cosine of negative 165 degrees. You should try it. Make sure you're in degree mode. Negative 0.46. And root 2 over 3 times the sine of negative 165 is a negative 0.12. And that is the I, imaginary part. Standard form. So now, how can I raise a complex number in trig form to an exponent? Raise it to a power. Z to the n power. How can I take that complex number, raise it to the n power? So here they've just rewritten it. They said, all right, complex number raised to some power. Well, it also is fairly simple. You just raise the modulus to that power, and you multiply the angle by that power. So they give me this number. They say use DeMoivres Theorem and figure out what it will equal when I cube it. Now this was given in standard form, 1 plus I square root of 3. Well, DeMoivres Theorem uses trig form. So we need to convert this to trig form. So over here, positive 1 in the real, positive square root of 3 in the imaginary. So we have 1 square root of 3. We can recognize this. 1, 2 square root of 3. That's a 60-degree angle, or pi over 3. We want to do it always in radians unless they tell us we're doing it in degrees. So there we have the values that we need to write it in trig form. It becomes 2 parentheses cosine pi over 3 plus I sine pi over 3. So this is the complex number, and they are wanting us to cube that complex number. No problem. DeMoivres Theorem says cube the 2. The modulus, 2 cubed, that's 8. Then multiply the angle by 3. Well, 3 times pi over 3 just gives us pi. Now there is our answer to what it is when we cube it in trig form. But since we started in standard form, let's go ahead and end up back in standard form and see what we get. Now I don't need a calculator because this is an exact value I can get. My angle is pi. My angle is pi. I'm right over here. And my radius, or my distance, is 8 from the origin. So I can write that. My real part is -8. My imaginary part is 0. -8 plus 0i is just the number -8. So my solution in standard form is simply -8. And your calculators have the ability to work with complex numbers if you have them in the right form. We're going to verify this with our calculator. So on your graphing calculator, go to your mode and change it into complex form right there. Instead of the real on this line, instead of the real, you can put it in complex form, a plus bi. And then it actually allows you to enter that complex number. So let's pull up my calculator here. Mode, I'm going to make sure that I am in the complex form, which I am down there. So I can get out of that. And I want to cube this. So parentheses, 1 plus square root of 3, I, and my I is located right above, let's see if I can read it, whoops, second, right above the decimal point. There's your I. Close my parentheses, try that again. Close my parentheses and cube that, raise it to the third power. And we should get -8, sure enough. So it worked out for us. That's a double check. That's not a method for doing the problem. All right, so let's try DeMoivres Theorem again. They say take this value and raise it to the 8th power. Again, if I start in standard form, I have to convert it to polar form, and then DeMoivres Theorem is pretty easy, and then I can just convert it back. Without a calculator, raising something to the 8th power would take a long time multiplying those all out. So let's try this. Negative square root of 2 over 2, so I've gone back, square root of 2 over 2, gone back. Then I have gone up in the imaginary direction, the same distance, square root of 2 over 2, to arrive at my location. So I need to figure out two things. I need to know what the radius is, and I need to know what the argument is, the modulus and the argument, or the angle to it. Well, that may not seem like anything special, a special triangle, but if you think a moment, those two legs are the same length. This is a 45, 45, 90 triangle. Or if you will, that angle is pi over 4. So that means this angle, the one we want, is 3 pi over 4. And I just need to get the radius out there, or the modulus. I can use the Pythagorean Theorem, so that would work. Or a little shortcut to that, if you remember your 45, 45, 90 triangles from geometry, you just take a leg. So I'm going to take a leg, square root of 2 over 2, and multiply it by the square root of 2. So a leg times the square root of 2 is the hypotenuse of a 45, 45, 90 triangle. Or use the Pythagorean Theorem if you so desire. Square root of 2 times square root of 2 is 2, over 2, 1. That value is 1. So I know that I have the complex number 1 for the modulus, cosine 3 pi over 4 plus I sine 3 pi over 4. And this I can use DeMoivres Theorem, raise it to the 8th power. Well, 1 to the 8th is just 1. Multiplying my angle by 8, 4 goes into 8 twice, 2 times 3 is 6, we get 6 pi, plus I sine of 6 pi. I want to convert it back to standard form. Well, if I just do a little diagram of this one, 6 pi, that's really just 3 full circles. 2 pi, 4 pi, 6 pi. I've just ended up back here, a distance of 1 away. So that is 1 in the real, 0 in the imaginary, or that is just the number 1. So you raise that number to the 8th power, the answer is 1. All right, we have learned how to multiply and divide complex numbers in trig form, how to raise a complex number in trig form to a power. Now we need to know how to take a root, a square root, a cube root, a root of a complex number. So we know what a root means. If I have 2 cubed equals 8, it means 2 is the cube root of 8. So that's all they're saying right over here. Something is the nth root of a complex number. Now, if your complex number happens to be 1, they're called the nth roots of unity. So what are the 8th roots of 1? Well, they're the 8 roots of unity. All right, right here is our formula. A little more involved than the others of how I find a root of a complex number. So here they have said r cosine theta plus I sine theta. If I want to take the roots of a complex number, so right there is the index. I'm going to take the nth root of it. 2 square root, 3 cube root, 4 fourth root, etc. So I take the root of the modulus, the root of the radius, pretty good, and then I divide my angle by the root, 4 fourth root, 3 for third root, etc. With one additional thing. It's not just dividing the angle. I have to add 2 pi k to that angle. And k has multiple values. The k value is going to start at 0, continue until it is 1 less than the power you are raising it to. So let's run through this formula to find the 4th roots of this complex number. Now, something that you can notice here, if I'm finding the 4th roots, that means my k is going to start at 0, 1, 2, end at 3, which means there are 4 4th roots of any number. There are 2 square roots of any number. We're familiar with that. What are the square roots of 9? -3 and +3. Both of those I can square and equal 9. There are 3 cube roots, 4 4th roots, 5 5th roots, etc. So if you want to find the 17th roots of a number, there are actually 17 numbers that you can raise to the 17th power and get the same answer. Okay, let's try this out. Example number 7. We have our formula where I'm supposed to take the 4th root of 5. So that's where I start. Now k equals 0. The 4th root of 5. And then cosine of my angle, pi over 3, plus 0. I'm doing this. 2 times pi times 0 would just be 0. Divided by 4. Plus I sine of pi over 3 divided by 4. With k equals 0, there's nothing to add to our angle. So if I take, and we'll take the 4th root of 5 later on, but if I take this problem, I get the 4th roots of 5 cosine pi over 3 divided by 4 would be pi over 12. Pi over 12 plus I sine pi over 12. That is the first 4th root of this number. So our second one, when k equals 1, well, it's the 4th root of 5, cosine of our angle, pi over 3, plus 2 pi times 1. K is now 1. So I'm back up here again. I have to add this to my angle. So 2 pi times 1 is 2 pi. Plus 2 pi, that is divided by 4. Plus, and the sign, the same thing happens. So let's see what we get here. 4th root of 5 cosine of, now if I take pi over 3 plus 2 pi, and 2 pi is 6/3. 1/3 plus 6/3 is 7/3 divided by 4 would be 7/12, or 7 pi over 12 plus I sine 7 pi over 12. There's our second answer. Now when k equals 2, the 4th roots of 5 cosine of our angle pi over 3 plus 2 times pi times 2. K is now 2. Well, 2 times 2 is 4. So that's 4 pi over 4. And then the sign, the same thing happens. So pi over 3 plus 4 pi. So 4 pi would be 12/3 plus 1/3 is, 12, would be 12/12. What am I doing here? Common denominator, 4 pi, so over 3, yes, 12 pi over 3. 12 pi over 3 plus 1 pi over 3 is 13 pi over 3, divided by 4, 13 pi over 12. 13 pi over 12 plus I sine 13 pi over 12. And our last one, k equals 3. So we still have the 4th roots of 5 cosine of our angle plus 2 times pi times 3, because our k is 3. So 6 pi. 6 pi, all divided by 4. All right. So in terms of thirds, we would have 18/3, 6 pi, 18/3, plus 1/3 is 19/3, divided by 4 is 19/12, 19 pi over 12. 4th root of 5 cosine 19 pi over 12, plus I sine 19 pi over 12. 1, 2, 3, 4. They're my 4 4th roots. Now we want to take these and learn something about the graphs of them when they are in standard form. So we're going to take each of these answers, which are in trig form, convert them to standard form, the a plus bi. So remember, all we need to do is distribute there. So calculator's in radian mode. And if we took our first and took the 4th roots of 5 times the cosine of pi over 12, we'd get 1.44. 4th root of 5 times the sine of pi over 12, positive 0.39 pi. So our first, our second is going to be negative 0.39 plus 1.44 I. Our third converts to negative 1.44 minus 0.39i. You may begin to see a little bit of a pattern developing. Our fourth is a 0.39 minus 1.44i. I want to look at the sketch of a graph of these complex numbers. So if we took a complex plane, real part, imaginary part, and we graph this, so I'm going to say there's 1 in the real direction, there's 1 in the imaginary direction to kind of get a scale going on this. 1.44.39i, 1.44.39i, there's the first one. Negative 0.39 up 1.44, there's our second one. Negative 1.44 down 0.39, there's our third one. And over 0.39 down 1.44, there's our fourth one. All of these lie on a circle. evenly distributed around that circle. Every single one of these is evenly distributed around the circle. And that fact is going to lead us to a shortcut of getting all these angles out here without having to run through our formula of theta plus 2 pi k each time. So here is how we can do it. If things are evenly distributed around a circle, a full circle is 2 pi radians. And if I have 4, because I'm doing 4th roots, I can divide that by 4 and to know how frequently they're going to occur. Well, that reduces to pi over 2. Every half of pi, these are going to occur. Now, if I find my first one, where k is 0, so I'm not adding anything to my angle, I'm just dividing my angle pi over 3 by 4, which gave me pi over 12. Right over here, it gave me pi over 12. That is my starting point that I then can just add a half a pi to, and I should generate all the others. Now, in terms of 12s, a half a pi would be 6 pi over 12. So if I take 1/12 plus 6/12, I get 7/12. If I take 7/12 plus 6/12, I get 13/12. 13/12 plus 6/12, 19/12. There it is. Quickly generating all the other angles, because the solutions will always be evenly distributed about a circle. Example 8. Find the cube roots of -1. They want us to plot them. That's what I did on the last one. I plotted it a little bit. Well, before today, if you were asked to find the cube root of -1, you could have come up with one answer, -1. That is true. But there are 2 more solutions to this. There are actually 3 cube roots of -1. -1 is going to be one of the answers. So let's see if we can try this out. Now, -1 is -1 plus 0i. But that's standard form. I need this in trig form before I can apply my method of finding all the roots. So if I take -1, so there's -1 in the real direction, 0 in the imaginary. Well, it's not hard to convert it to the trig form. That distance, the radius is 1, and the angle is pi. So it is 1, comma, cosine pi plus I sine pi. There's the number that we are wanting to find the cube roots of. And there will be 3 of them. Okay, so the first one, to get number 1, I'm going to take the cube root of 1, cosine of my angle divided by 3, plus I sine my angle divided by 3. There's my first one. Now, to know what to add to my angle, instead of running through that formula of different k values, which you could, but in order to know what to add to my angle, I know my full circle, 2 pi, is going to be divided evenly 3 ways, 2/3 pi. So that is the value that I just need to keep adding to this angle until I have my 3 solutions. So for number 2, it's the cube root of 1, which happens to be 1. So I guess we could write it as just 1 here. 1. Cosine of, well, 1/3 plus 2/3 is 3/3, or just pi. Plus I sine pi. There's my second answer. I want my third answer. Cube root of 1 is 1. Cosine of, well, take pi and add another 2/3. 1 is 3/3, plus 2/3 is 5/3. 5 pi over 3. Plus I sine pi over 3. Now, I want to convert these into standard form. I'm going to plot them. So if you took the square root of 1, the cube root of 1, which is 1, 1 times the cosine of pi over 3, and again, make sure you are in, oh, we don't need to do a calculator. You don't need to be in radian mode because we have a special angle for that. Pi over 3, that's a 60-degree angle. 1, 2, square root of 3. Right there's my pi over 3. So the cosine of pi over 3 is 1/2, and the sine of pi over 3 is square root of 3 over 2 in the imaginary direction. Okay? Pi. Well, if I think about that for a minute, the angle of pi is right there. The radius of 1, that's -1 in the real direction, 0 in the imaginary direction, or there's that answer that we knew already, -1. There's one of the additional ones we didn't know before. 5/3 pi. Well, 5/3 is 1/3 less than a full circle. We're way over here. 5/3 is over there, 60-degree inside that. Square root of 3, negative square root of 3, 1 and 2. So the cosine of that one is 1/2. And the sine of that one is negative square root of 3 over 2 in the imaginary. So there are the 3 cube roots of -1. I want us to plot these things. So if I plotted these all around my unit, or my complex plane, real and imaginary over here, over 1/2, up square root 3 over 2, so right about there, back 1, right about there, over 1/2, down square root of 3, right about there. So they should be evenly distributed around the circle. If you use your imagination, those are evenly distributed around the circle. Last one. Find the eight roots of unity. Remember, unity means 1. And yes, there are going to be 8 of them. Okay? Once we get this down, takes a little bit of time, but it's not too hard. First, trig form. So if I take a positive 1, 1 plus 0i, and put it in trig form, my radius is 1, and my angle is 0. So I have 1 cosine 0 plus I sine 0. There's my trig form. And we are going to be taking the 8 roots of this thing. So I need the 8th root of 1, which is 1, and then the cosine of my angle divided by 8. Well, 0 divided by 8 is still 0. Here's my first answer. Now, if I have 8 of them, and 2 pi is a full circle, divided into 8 parts, I get pi over 4. I need to add a quarter pi to these each time. 8th root of 1 is 1. Cosine of 0 plus a quarter pi is a quarter pi. Plus I sine pi over 4. My next one. 1 cosine of, add another quarter pi. 1/4 plus 1/4 is 1/2 pi. Pi over 2. Plus I sine pi over 2. My fourth one. 1 cosine 1/2 plus 1/4 is 3/4. Takes a little while to write, longer to write than to actually figure it out. Cosine 3/4 plus a quarter is 1 pi, so I'm at pi. Plus I sine pi. 1 cosine, add another quarter, so I'm at 5/4. Get my next answer. 5/4 plus 1/4 is 6/4, which reduces to 3 pi over 2. I have 1, 2, 3, 4, 5, 6, 7, one more. Cosine. So 3 over 2, or 6 fourths plus 1 fourth is 7 fourths. 7 pi over 4 plus 9 sine 7 pi over 4. And there are the 8 solutions. Now these could all be converted into standard form, numbers that we maybe are used to before. If I take this first one, and you could run it through a calculator, but these are actually exact values that I can get very easily. Cosine 0, well, remember on the unit circle, it's the value of cosine, comma the value of sine. So cosine is 1. 1 times 1 is 1. And sine of 0 is 0. 1 times 0 is 0. 1 is one of the 8 roots of 1. Well, we knew that. 1 to the 8th power is 1. That's just one of the answers. Then if I did the next one, the pi over 4, well, that's a special triangle as well. 1, 1, square root of 2. And so 1 times the cosine of that is 1 over square root of 2. 1 times the sine of that, 1 over square root of 2. That's the next one. If we keep going through, this one would end up being I. This one would be negative square root of 2 over 2. I guess I rationalized this one, didn't I? So I could rationalize the one up here into positive square root of 2 over 2. That's after it's been rationalized. Negative square root of 2 over 2 plus square root of 2 over 2i. And this next one is a negative 1. Negative 1 to the 8th power is also a positive 1. This is a negative square root of 2 over 2 minus square root of 2 over 2i. This one is a negative I. And this one is square root of 2 over 2 minus square root of 2 over 2i. Let me look at this one for just a moment so we can see where are we getting a negative 1, or let me not do that. Let me do the negative I. Look at this one. How are we getting negative I out of this answer? 3 pi over 2. If I did a sketch for the angle 3 pi over 2, that's the quadrantal angle right there. Well, its ordered pair is 0, negative 1. The value of cosine is 0. The value of sine is negative 1. So 1 times 0 gives me 0. 1 times the sine of that angle is negative 1. So 1 times negative 1 is negative 1 pi. There it is, negative 1i, or negative I. You could verify if you wanted to on your calculator. You could take, here is this one. I raised it to the 8th power, and sure enough, it equals a positive 1. So there are 8 roots of 1, or of unity. All right, you can look in your syllabus for what the assignment is on Chapter 6, Section 6, 6.6.